Hello again. So today's lecture we're going to talk about measuring data similarity, measuring similarity between different data sets, different data points. This is just an introduction to some concepts that we'll reuse over and over, and we may introduce other similarity measures later on. But the idea is just to, now that we've talked about definition of what data is and what different types of data there are, a lot of data analysis, machine learning, clustering, pattern recognition is going to be saying, are these 2 points that we have, 2 data points, whether it's representing people and their biographical information, or 2 images, or 2 states of your car, or 2 different sensor readings, whether those 2 data points are similar or different. It's a really fundamental thing that we use really so much. It's almost everything comes down to being based on similarity, dissimilarity, and probability metrics between sets of points. So we're going to define these in various different ways for different types of data that we've talked about, and just set the groundwork here. So what are we talking about in terms of terminology and words? We're going to say often similarity and dissimilarity, or I might say distance, right? You might say proximity, right? These are all kind of words that will be used kind of in the same way. Obviously, if 2 things are similar, then they are close to each other, right? And if they are dissimilar, then they are far from each other, or their distance is high, right? So the more similar the objects are, the higher a similarity score would be, and the higher a distance score is, or dissimilarity score is, then the further apart they are, the more different they are, right? Right, so similarity and proximity could be used interchangeably. So why is this important? It's important for many reasons, because so many methods kind of represent things this way, but it really comes down to thinking of data points like we have, you know, 2 dimensions like we talk about in our data set, right? And you've got your table, and maybe you've got multiple dimensions, but for simplicity of drawing it, you'd have all of these, right? And we have many, many thousands of data points and some number of features. Usually the number of features or dimensions here is a smaller number of data points, right? We could even do this in 3D, so let's give us y1 and y2, right? And then literally when we're talking about data points, it's not really that complicated. We're saying, you know, is this point far away from this point? What is the distance, right? That's a spatial way of looking at it, right? So this is a spatial view. You don't always want to use a spatial view. One reason, why wouldn't give me anything but 5 reasons why you might not want to do that. Good to think about that, right? It could be that these points are easy to visualize, and you want to see, you know, trends in the points going up this way, and your money going down that way, and the economy going this way. But it could be that they're not very easy to visualize, right? What if these are genes? You wouldn't really be able to see some correlation amongst them in any reasonable way, and there'd be millions of dimensions. So a spatial kind of metaphor here wouldn't really be useful, right? So think of these, whether it's proximity or distance or similarity, these are just useful concepts or metaphors that we use to help us get our tiny human minds around it. But what it comes down to is numbers and how to measure whether they are close to each other or not, right? So let's make it much more numerical. So we have our data matrix that we start with, right? So we have our rows of data and our columns of features, right? And any pair of points, we could say, well, what's the distance between these 2 points, right? So I might want to say, what's the distance between this point and this point, right? I guess given the next figure, it's this point, right? If I wanted to say D3, 1, I'd be saying, what's the distance between these 2 points? And then I put down the distance here. So obviously there aren't as many values as there are in the full matrix of data. You'd end up getting this triangular matrix, distance matrix, if you computed the distance between every single point and every other point. You'd have a triangular matrix. That's just kind of a fundamental thing about the numbers. And this doesn't have to have any spatial concept, right? We're just saying, okay, here's all these things, and now the real question is, what is this function? Because I shouldn't use D, because we're using D somewhere else. What is this function here on xy that gives us this thing that we call distance, right? And distance will actually be just a particular subset of that. So how could we do this? We could have, if we think about our data vectors, there's just 2 binary vectors, right? Well, for binary types, right? So for binary data, where all our data are just zeros and ones, right? We're going to have 2 vectors, and we want to say, are they close or far? Right? Are these vectors similar, if that's the metaphor you want to use? Close, you want to use distance. So the dot product's kind of one of the fundamental ways you can do that. You can compute just the combination of all these values, right? So the dot product's just going to give you, obviously, the multiplication of and sum of all the components of these, right? So we write it in vector notation like this. T means transpose. If you don't remember your linear algebra, you should go study it. So essentially, this is equivalent to saying I'm going to sum over all element I, right? And I here is the index 0, 1, 2, 3, 4, to whatever number you're going to. And I'm multiplying them together and then summing it, right? So when I say x transpose t, then I'm giving you, a matrix, 2 vectors like this, and then doing that. Is that the right way to do it? Rows, columns, columns, rows, right? Right? N by 1, 1 by n. No, that would give me n by n, right? Right, so you gotta get the other way around. Right, so you transpose it, you're saying that you're getting the vectors like this, and then it comes out to the right size, right? Because all we want here is a single number of dimension 1, which is just this distance, right? And so by the fact that we're saying x transpose y, that means that our assumption is that these vectors are always vertical, that they're row vectors, which is true for our data, right? Because we had y1, y2, right? And we have these rows here. So we're assuming that a data vector of x's is a column, and then we rotate it and we get us this transpose. So that's just what dot product is. And obviously, what would this give us? This would give us a measure of whether they're near each other based on how much agreement there are, right? If the vectors are binary, then when there's a 1, you're gonna have a 1 added. When they're 0, you're gonna have a 0 added. When they're different, you're gonna have a 0 added, right? So you're only gonna get increments when they have shared numbers, right? So the dot product essentially is saying how many features do these two vectors agree on, right? If we normalize it by the geometric mean, just take the square root, then we get something that's a bit more uniform. and kind of on a scale, so that we know that the scale is based on the actual size of the vector. Another similar thing to do here with binary vectors is called the Hamming distance, where you literally count the difference between the binary vectors, and you say that if they're in disagreement, then you count it, right? So kind of the inverse of this dot product. So rather than just adding ones where they agree, now you subtract them, and whenever it's not 0, you add 1. And so this would be all the ones where they disagree, right? So these both give you kind of different numbers, but they could be useful depending on what you're using. Depending on what you're representing with your vectors, you might want to say, well, how much they agree on these things, how much they disagree. You could put these together and weight them, right? You could have the dot product plus the Hamming distance and weight them so much. So I want to give, 60% weight to the ones that all the times they agree, and 40% of the times they disagree. And then you'd have this kind of weighted kind of score on how similar they are. And so one final binary measure we'll mention here is tanamotor measure, which kind of combines the both of the ones we talked about before. So it has a dot product on top, and then it normalizes that. So, right, this is the sum of all the ones that agree, and normalizes it by that count plus this difference of all the ones that are on versus subtracting them from that agreement. So it's kind of ratioing by as a ratio of how many ones there are in the first vector versus how many ones there are in the second vector, and subtracting the difference, and then normalizing the ones they share. So, if you have lots of zeros on both of them, you won't be penalizing in here and making a very small score. Whereas if they, right, if only x's and y's are like thousands of bits long and only have, a few dozen ones in them, and then you've got 5 ones in common, now you're getting this 5 over, 50 or 60 type score rather than 5 over thousands, right? So it'll give you a better measure if you have this case. If there's if ones are rare, essentially, in the vectors. So they all have their different kind of places. Okay, so that's kind of some things for binary types and contingency tables. This is also used for binary types, but it kind of comes up in a lot of other ones. This we'll see again and again, but this is kind of the first time you'll see it here. Contingency tables is a very simple version of it. The basic idea is you have 2 data points, x and y. In this case, they're binary, so you have 0 and 1, and you want to name all the different scenarios about whether they agree or not, right? So we've been looking at just like sums of how many agree or not, but here you could just give a name to each of them. So M1 is when both of them, it'd be for the whole vector, right? So it'd be the sum of how many of them agree. And then you'd have the sum of all the ones where, y was 0, but x was 1, and the sum of all the ones where x was 0 and y was 1, and the sum of all the ones that are 0, right? So the ones we've looked at already essentially cover these 2 cases, but if you want to specifically cover all 4 of them, you can do this in a more general way using contingency table. And then there's some other scoring coefficients that people use to compare binary vectors, which combine a bunch of these in a more subtle way, right? So with a simple matching coefficient, equal weight is being given to zeros and ones, so you can count either of them. They're matching on anything, so it'd be matching on zeros or matching on ones, just basically saying really how similar they are, right? This is really quite feeling like it's an intuitive similarity idea, right? Because if they have the same number, then the score will be higher, right? Whereas the Jaccard coefficient only looks at whether they are ones. So this gives you something very similar to the, at least in behavior, to the dot product, but it'd be normalized differently over these other cases. Right? These particular formulations have their own kind of benefits, right? They're always less than 1, which you can work out, and they have the nice property that if they equal 1, then that means they're the same, right? So that can be a nice property that you might want to have in your scoring function, but you might have to design your own kind of metrics like this in some cases, right? And if you want to get like simple distance, like Euclidean distance, then you kind of have these 1- versions of these. So those can be useful as well, especially when you're doing like pattern matching and kind of scoring. So we're talking about binary types, so assume now we want to convert to a nominal type. Right, so nominal types, remember, are ones where we have a qualitative kind of behavior. So hair color, red, green, blue. I like blue. So red, green, blue, black, brown hair, right? And they don't really live in order, right? And so they're all values that can be compared. You might want to say distance between them. You're only going to be able to do these kinds of comparison distances where you can say how many of these values do you have in common. So the ones we've been talking about are perfect for that. Of course, those are binary, so if you wanted to do that, you could turn it into a what we'll call a one-hot encoding, where you say you take all of the hair colors, right, and every hair color has its own, all of the values in every hair color has its own feature. I should do this neater. I meant to do it as an underscore, sorry. Right, and these all just become features, and then you have your people in your data set, and it would just have only one of them would be true, right? And so based on which color they have, I guess we could have some common hair colors too, then you would you'd assign it, right? So you're basically exploding the number of features by the size of this particular one, but then you get a feature for each one, and it's meaningful there, right? And then all these distance measures would work. You'd say, well, how similar are their hair colors? Like, well, are they agreeing or not? Or you can do other things. Maybe you could even group them and say, well, you know, natural ones and fake ones, right, or colored ones.